High in the Peruvian Andes, the citadel of Machu Picchu guards centuries of history. It also guards a persistent rumor, the lost gold and silver of the Inca Emperor Pachacutec. In 2012, two French explorers stepped forward with a bold announcement. While surveying the ruins, they claimed to have discovered a hidden sealed door, perfectly integrated into the stone structures. According to their 3D underground scans, a gold-plated staircase sat just behind that wall. They reported that it led down to a massive burial chamber filled with silver artifacts, accompanied by 10 smaller cavities housing child mummies. The explorers demanded immediate permission to excavate the site. The Peruvian Ministry of Culture outright blocked them, viewing the request as an attempt at glorified, destructive looting. We have a standoff between a pair of self-proclaimed discoverers and a highly protective government. Are we looking at a suppressed archaeological triumph, or simply a high-tech hoax? To find the answer, we have to bypass the sensational headlines and look at exactly how they gathered their underground data. The French team built their case on ground-penetrating radar. It pulses electromagnetic waves downward into the Earth. When these waves hit a boundary between different materials, like soil, rock, or a void, they bounce back. The radar records these echoes to map out changes in density. But density is the only thing it measures. GPR cannot see color, and it is chemically impossible for the radar to distinguish between common rock and precious metals like gold or silver. It also cannot render detailed, complex shapes. A void in the dirt will register, but the intricate physical contours of human remains or mummies will not appear on a scan. This split-screen diagram illustrates the fundamental physics trade-off of GPR. High-frequency antennas use tight waves to produce high resolution, but they can only see a few feet down. Low-frequency antennas stretch the wave to penetrate much deeper, at the severe cost of visual clarity. The explorers claimed they mapped chambers 20 meters below the surface. Penetrating that deep into mountainous terrain requires a low-frequency antenna, typically operating between 25 and 50 megahertz. At that specific frequency, the returning data is incredibly crude. Instead of clearly defined stairs or burial artifacts, the output resolves into a blocky, unrecognizable blur. The explorers took these pixelated, simple rectilineal anomalies and presented them to the public as confirmed royal treasure. The goal was to force Peru's hand into granting an excavation permit. The historical record further dismantles the claim. Machu Picchu was a relatively minor estate holding, roughly 700 people, not even large enough to house an emperor's full retinue. It is an incredibly unlikely location for a vast imperial tomb. The explorers weaponized the inherent complexity of a scientific instrument. They used radar as a prop to manipulate public hope, rather than to conduct rigorous science. Now look at how actual archaeological discovery works, roughly 70 kilometers away in the city of Cusco. Here, researchers recently verified the Chincana Tunnel Network, a 1,750-meter passage connecting the Temple of the Sun to the Sacsayhuaman Fortress. Archaeologists Jorge Calero and Mildred Fernandez did not start with a radar gun. They started with documentation, specifically relying on 17th-century Jesuit texts that explicitly described underground streets crossing the city. Before turning on a computer, they performed physical acoustic tests. They walked the suspected path, striking metal plates against the ground every 50 centimeters to locate deep, echoing resonance. This GPR data chart shows how they properly applied the technology. They deployed the radar to map the dimensions of a massive 2.6-meter-wide structural void beneath a street surface, confirming what they already suspected. Their scan aligned perfectly with the known physical features of Inca architecture in the area, specifically the massive stone-lined walls and carved beams near the Sacsayhuaman complex. Genuine archaeological breakthroughs start with a strong foundation of historical evidence. Technology is then used to confirm structural realities, not to chase shiny myths. In the field of archaeogeophysics, a single radar scan is never enough to justify taking a shovel to an ancient site. This diagram shows the required multi-instrument approach. Scientists cross-reference GPR data with complementary tools like electrical resistivity and gradiometry. An anomaly is only taken seriously if it appears across multiple independent sensors. Dressing up treasure hunting in technical jargon has real consequences. Shouting about buried gold incites illegal looting, disrespects local heritage laws, and drains time and resources from the people actively trying to protect these sites. The Inca Empire left behind breathtaking megalithic engineering that has withstood centuries of harsh weather and seismic activity. Genuine wonders still wait beneath the earth. Modern technology is a highly capable tool when applied correctly, but rigorous verification is the only path to real discovery. The truth is found in the data, once you filter out the noise. The myth of lost gold has drawn explorers to the Andes for centuries. Machu Picchu serves as the epicenter of this imagination, a mountain citadel that remained hidden from Spanish conquerors for generations. In 2012, David Crespi, a French engineer stranded at the site by rain, noticed something out of place. He saw a gap between heavy stones that had been filled in without mortar, looking like a purposefully sealed entrance. Crespi contacted Thierry Chamin, a French explorer who brought ground-penetrating radar to scan behind the wall and see what lay inside the mountain. A tourist's hunch grew into a publicized hunt for what was presented as a significant archaeological find. Using the radar results, Chamin claimed to have found a burial chamber 20 meters deep. He believed it held the remains of Pachacutec, the emperor responsible for the empire's greatest expansion. The scans reportedly showed gold-plated stairs, a trove of silver artifacts, and smaller tombs for children. Before any digging began, the Peruvian Ministry of Culture halted the project. They refused to grant permits, citing the risk of structural failure within the World Heritage Site. This decision left the public to choose between two versions of the story: a government-led cover-up or a high-tech illusion. Scientific pushback was immediate. On forums and in academic reviews, geophysicists pointed out that the explorers' claims ignored the physical limits of the technology. This shows how ground-penetrating radar works. It measures conductivity to find anomalies, but doesn't generate color images or identify metals. Depth limits resolution. Seeing 20 meters deep requires a low-frequency antenna, turning the data into crude, indistinct shapes. Chamin's team likely detected a natural geological void or a rectilinear anomaly. They then built a narrative of a gold-filled tomb on top of those blurry blocks. In near-surface geophysics, making a definitive claim from a single instrument is considered irresponsible. You need secondary data from tools like electrical resistivity for verification. The incident shows how confirmation bias can weaponize a tool to validate a fantasy rather than seeking the raw truth. 70 kilometers away, in the city of Cusco, a different team demonstrated how techno-archaeology is supposed to look. The Chincana Tunnel project didn't start with a radar scan. They started with a 17th century chronicle written by a Jesuit monk. The search began at Sacsayhuaman, where massive, interlocking stone blocks formed the base of a historic fortress. The team started with simple acoustic testing. By striking metal plates every 50 centimeters and mapping the hollow echoes, they found the initial evidence of tunnels. They only used radar to confirm what they already suspected. The scans proved a subterranean network nearly 2 kilometers long, connecting directly to the Sun Temple. By combining old texts, acoustic physics, and targeted radar, the team proved a centuries-old urban legend was actually a tangible feat of engineering. These two approaches represent a distinct divide in archaeology. One team started with the conclusion of treasure and worked backward. The other started with a question and used tech to find the answer. The focus on glittering physical treasure often distracts from the actual innovations of the past. Understanding Inca urban planning reveals how they engineered a city to connect its most sacred sites beneath the streets, a detail often lost in the search for precious metals. Sensational claims can be physically dangerous. Digging into ancient monuments based on flawed data risks the very structures people claim to be discovering. Real breakthroughs require a multidisciplinary approach and a willingness to follow the data, even when it isn't glamorous. Ground-penetrating radar reveals the complex, true narrative of our history, a story that remains significant long after the hunt for gold is over. High in the Peruvian Andes sits Machu Picchu. For over a century, popular culture has framed these ruins as a pristine, isolated, lost city, secluded from the outside world. The accepted history says the site was a royal palace, built by Emperor Pachacuti around the year 1438 to serve as an elite mountain retreat. The problem? The Incas left no written records. To arrive at the 1438 date, researchers relied entirely on 16th century Spanish colonial documents. These are biased, second-hand accounts written by the colonizers themselves, often decades after the events, with clear political motivations. For centuries, our foundational understanding of the Inca Empire has been dictated by the word of the people who conquered them. Modern archaeology is now bypassing these texts. Instead of trusting the conqueror's ledger, researchers are asking the physical site for answers. Using samples of bone and teeth from 4 cemeteries around the site, a team analyzed the remains using advanced mass spectrometry radiocarbon dating. This measures the decay of carbon isotopes to determine an object's exact age. The results reveal a massive discrepancy. Physical evidence shows the site was occupied starting around 1420 AD, nearly 2 decades earlier than written history claims. As the timeline scales back, the implications grow. This gap suggests a much earlier start to their imperial growth. These physical remains have done what the documents couldn't. They've provided a timeline based on biological fact, contradicting the stories told by the Spanish. This science also shifts the focus from the emperors to the people who actually lived here year-round, the servant classes, known as the Aclacona and Yanacona. In 1912, the Yale Peruvian Scientific Expedition uncovered 174 graves of these retainers. Curiously, they were buried with a massive variety of pottery styles. Pottery can be traded across long distances, making it a poor tool for tracking human origins. To find out where these people actually came from, researchers turned to genetic testing. They sequenced the DNA of 68 individuals found at the site, looking for the genetic signatures of their homelands. The diversity was staggering. Only 7 individuals were local to the highlands. The rest traced lineages to the coast, the Amazon, and as far as Ecuador, Colombia, and Brazil. The movement was empire-wide. In Argentina, a child's DNA traces back to the northern Peruvian coast. The genetic evidence places Machu Picchu at the center of a massive geographical web, a cosmopolitan intersection for lineages from across South America. Bone analysis reveals that these diverse servants lived surprisingly stable lives. They were buried with equal care, showed no signs of malnutrition or heavy labor, and formed families with people from distant regions. These biological records detail a bustling, integrated community, diverging sharply from the image of a silent, secluded fortress. This was a vibrant, genetically diverse epicenter of an empire that began its rise far earlier than any colonial text claimed. Through genetics and radiocarbon dating, the anonymous residents of Machu Picchu are finally speaking for themselves. Their bones are correcting the history books that the conquerors wrote. This is the iconic view of Machu Picchu, a heavy stone citadel resting on a narrow ridge high in the Peruvian Andes. Building at 8,000 feet creates an engineering nightmare. The site faces 2 massive geological threats: torrential tropical rains and constant seismic activity. By the standards of conventional civil engineering, these massive stone structures should have washed into the river valley centuries ago. They remain standing because the temples and houses tourists see on the surface only account for 40% of the actual construction. Understanding how this city has survived for 600 years requires looking beneath the surface, into the invisible 60% of the site buried in the mountain itself. The massive agricultural terraces surrounding the city provided farmland, but their primary engineering role was defending the ridge against erosion. Excavations revealed these terraces are 9 feet deep. 3 feet of topsoil absorbs the rain. Beneath that, sandy gravel filters and slows the water. Finally, a foundation of jagged granite waste rock lets high volumes of water safely exit into the mountain. This tiered, spongy architecture functions as a massive shock absorber, diffusing torrential Andean rainfall before it can compromise the mountain's structural integrity. Beyond managing rainfall, the city required a constant supply of fresh drinking water without flooding the terrace drainage systems. Inca engineers mapped the flow of a single mountain spring and predicated the city's entire urban grid upon its specific yield. A gravity-fed canal carries the spring water laterally across the upper terraces. Reaching the urban sector, it feeds 16 cascading fountains, stepping the flow down through the religious and elite districts. This continuous circulation system provided for the population while dissipating the destructive energy of the falling water as it moved down the staircase elevation. At the deepest point of the excavation sits the natural geological bedrock, hiding the site's most significant engineering advantage. Satellite surveys show that the city was built directly over an X-shaped intersection of massive tectonic fault lines. These faults provided a natural quarry of granite, already fractured by the Earth's movement, significantly reducing the labor needed to build the city. Because the stones were pre-fractured and fitted without mortar, they dance during earthquakes, settling back into their original locks rather than collapsing. These tectonic fractures also provide an infinite natural drain, funneling all excess surface water deep into the earth. Returning to the macro view, the site reveals itself as a sophisticated example of geohydrological engineering. The Incas secured this ridge by integrating the mountain's natural hazards directly into the city's design. Earthquakes and torrential rains, the biggest threats to a mountain city, became the primary sources for building materials and structural drainage. This infrastructure functions as a biological system, operating as a functional extension of the mountain itself. Machu Picchu remains intact after 600 years because it processes the chaotic forces of the Andes through the 60% of the site we cannot see.